Let's see equation of a longitudinal wave. Sound is a longitudinal wave, and so far we have developed equation of a transverse wave in a rope string, and that was given by this y equals to a sine omega t minus kx. This is the equation of transverse wave. What happens in transverse wave? You know that if you have a particle at a distance of x from the source, then at time t, if it is found over here, then y is given by this equation. This is something which we know from the detailed method for transverse wave. Using same concept, we'll develop equation of a longitudinal wave. In transverse wave, what is happening? All these particles, they are oscillating perpendicular to the direction of wave propagation. Wave is traveling in this direction. This is the wave velocity v. Wave is traveling in this direction, and all the particles, they are executing simple harmonic motion perpendicular to this direction of propagation. Whereas in longitudinal waves, wave is traveling in this direction, and medium particles, they are also executing simple harmonic motion in the same direction. So if you take air molecules and this is the source, from the source you have, let's say, a particle at a distance of x. We need to find its position at time t. Now, wave is traveling in this direction with velocity v, and this particle is executing simple harmonic motion like this. Its motion is oscillatory, simple harmonic motion in this form, in the direction of wave propagation. Whereas over here, this particle is executing simple harmonic motion in this form. It goes up, comes back down, and moves to the same position. That's how it oscillates in transverse. That's how it oscillates in longitudinal waves. Now, in this case, transverse displacement was called y, and position of the particle was defined from the source by this number x. Since in longitudinal case, oscillations are also happening along the x-axis, we say that if at some point particle is found, let's say, at this position, this is the mean position, which is at a distance of x. Remember, what was x? X was mean position of a particle which is at a distance of x from the center, from the source. This is the mean position. What is y? Transverse displacement from the mean position. At some time t, this particle is found over here. In this case, that's how it oscillates. At some time, you found that this distance is s. For longitudinal displacement, we'll be using s. This is the direction of wave propagation. What is this? This is the mean position, which is given by x from the source. But at time t, you found that this particle is over here. Now, what is capital A? Capital A is the amplitude. Maximum which this particle can move, the amplitude part. In this case, this is the amplitude. From its mean position, it can move this much only. That's the maximum. This amplitude will define as S naught. A becomes S naught, Y becomes S, and this gives us equation of a longitudinal wave in this form. S equals to S naught sine omega t minus kx. Where everything is same, what is omega? 2 pi upon t, which is also 2 pi f. Your k is angular wave number, which is 2 pi upon lambda. Everything is same as we have done in transverse. Same steps we used to develop this can be used for this equation also. This is the source. Everything is known about source. It is oscillating in this direction, and this information is transferred by the wave along the x-axis at this rate v. So by the time information arrives at this, S is what? Longitudinal displacement. Write down this point. S is longitudinal displacement. S is longitudinal displacement from the mean position inside the bracket, which is at a distance of x from the source, bracket closed, at time t. S is longitudinal displacement of this particle whose mean position is at a distance of x from the source, and this longitudinal displacement is found at time t. What is S naught? S naught is amplitude. What do you mean by amplitude? Maximum displacement from the mean position. Write down, S naught is the maximum longitudinal displacement. S naught is the maximum longitudinal displacement. Now, when we write equation of a longitudinal wave in this form, then we have a problem with this. When you consider a transverse wave, you have a rope and you start oscillating one end, you can see all these oscillations. You can see the shape of rope. But if you consider sound wave, then you know that in sound, energy is being transferred, information is being transferred with the help of medium, air molecules. And we cannot see these air molecules. We cannot see their displacement. They are so tiny, there is no way you can observe them. So what we notice, what is that which we can feel? The thing which we can feel is called change in pressure. Instead of representing sound wave in terms of displacement form, this is called displacement form. Instead of developing equation of sound wave in displacement form, we go for its equation in the form of pressure wave. So if you write pressure wave, equation of sound wave, then we write P equals to P naught cos of omega t minus kx. This is displacement wave equation. Displacement wave equation. The same thing is when represented in terms of pressure is given by P equals to P naught cos omega t minus kx. We are representing sound wave with the help of this as well as this. Without proof, I'm giving you this equation. For this, I've already given a proof in the form of transverse equation. From this, I'm giving you this direct proof. If somebody is interested, we can discuss this, how to arrive at this. Not a difficult task, but we don't need that right now. So, let's discuss all the terms. What is P? It's not pressure. What is P? This is change in pressure. Change in pressure at time t at the position x. Over here, when sound travels from source and reaches this position, then at time t, change in pressure is given by small p. Now what do I say change in pressure? Even if you say nothing, if source does not produce any sound, you know that atmospheric pressure is already present. So this is not the pressure, remember. This is what? Change in pressure. What is x? Position. We are not interested in position. We are interested in what? S. What is S? Change in the position. From this, it moves to this position. So what is S? Change in the position. Similarly, P is not the pressure. P is change in pressure at time t at position x. Write down this. Small p is change in pressure at position x and at time t. Change in pressure at the position x at time t. Now what is P naught? P naught is what? Amplitude. This is now pressure amplitude. What do you mean by pressure amplitude? This is the maximum change which can take place at this position. Write down. P naught is pressure amplitude. P naught is pressure amplitude. That is, at any position, maximum change in pressure which can take place is given by P naught. You will understand meaning of this P naught with the help of this information. If I say what is the actual pressure? P actual at time t at this position. P actual at time t at position x, then it will be P atmospheric pressure plus small p. Now understand this. Suppose somebody gave us that P atmospheric is 10. Just take this P ATM as 10. Just to understand the whole concept. This is 10. And I given you P naught, pressure amplitude. This P naught is 3. That means what? If no sound wave propagates, then everywhere pressure is equal to what? 10. If you produce a sound wave, then maximum change in pressure which can take place is what? 3. What is 3? This is the maximum. you will find change in pressure as 1, 1.1, 1.5, 2.1, 3, but not 4. This is the maximum change in pressure which you can find. At some time, you found that this P is coming 1. Pressure has increased. Small p is coming 1. Then what is the pressure over here? You will say 10 is already there, and due to the sound wave, pressure has increased by 1, and therefore total pressure becomes 10 plus 1. Now, remember, this P is not always positive. Look at this cos. Cos, becomes positive, negative, positive, negative. So when this small p, at some time, let's say it becomes minus 2. Maximum is what? 3. That means it will vary from minus 3 to plus 3. Small p is not pressure, is what? Change in pressure. So when I say small p is minus 2, if I say small p is minus 2, that means pressure has decreased. So once this thing becomes minus 2, you will not use negative sign over here. That negative sign is already inbuilt. Once this small p becomes minus 2, pressure will be what? 10 minus 2. That is what? 8. So, actual pressure at time t at a position given by x will be what? Atmospheric pressure plus p. It's something like this. Try to understand the whole thing in this form. If I ask you, what is the actual position of this particle? Actual position of this particle with respect to source. If we write that with actual position of this particle at time t with respect to source, then answer will be what? X plus s. Suppose this is 10. This is 10, and you found at time t that this particle is 2 meters ahead. Then what is the actual position? 10 plus 2. That is what? 12. Now, this is 2, but after some time, you will also find it here. It can oscillate between these 2 points, plus S0 and minus S0. So its position will vary. That's how you will find actual position with respect to source. That's how you will find actual pressure at any point. Now, this P0 and this S0, they are related to each other in this form, which is an important result for competitive examination. And remember it like this. P0 is B K S0. Pressure amplitude, bulk modulus, K, angular wave number, and S0 is what? Displacement amplitude. Displacement amplitude. It's an important relation. Remember it in this form. P0 is what? Bulk modulus of the medium. If you consider air, then you need to go for bulk modulus of air multiplied by angular wave number multiplied by maximum displacement in the displacement wave equation. This and this, they both represent a longitudinal sound wave, but they are different versions. They are representing same thing, sound wave. Somebody, if can see the molecule oscillating, air molecule oscillating, he will find that equation of this particle, displacement equation, is given by this thing. If you place something which can measure change in pressure at the same position, then that change in pressure will be measured with the help of this equation. And notice one important thing. If this is sine, look at this. This is what? Cos. What is the phase difference between sine and cos? Pi by 2. Write down the important statement. phase difference between displacement wave equation, phase difference between displacement wave equation and pressure wave equation, displacement wave equation and pressure wave equation for sound is pi by 2, is pi by 2. What is the meaning of pi by 2? Let's try to understand this. Pi by 2 means if an oscillator is present over here and another oscillator is at the amplitude, we say that there is a phase difference of what? Pi by 2. Something at the mean position and the other thing at the amplitude, that is called what? A phase difference of pi by 2. Which means what? Suppose for a given x, you found that this whole thing is coming 0. This whole part, omega t minus kx, is coming what? 0. If this whole thing is coming 0, then sine 0 is what? 0. S is becoming what? 0. That means this particle is right at this location only. It is oscillating, and at some time t you found that it is over here. This whole thing becomes what? 0, and you found that it's over here. Now once omega t minus kx is 0, if you put it in this equation, then what is cos 0? 1. That means what is P? P naught. What is P naught? Maximum change in pressure. So when displacement of the particle is 0, you are observing maximum change in the pressure. That's the meaning of a phase difference of pi by 2 between displacement wave and pressure wave. Again, if at some point you found that this omega t minus kx, this whole thing, it becomes pi by 2. Omega t minus kx becomes what? Pi by 2. What is sine pi by 2? 1. That means S is coming S naught. This particle at that time will be observed over here. Maximum displacement from the mean position. So when this is pi by 2, particle is observed over here. But what about pressure? Omega t minus kx, it becomes what? Cos pi by 2. And what is cos pi by 2? 0. So what is P? 0. That means when particle is at the amplitude, change in pressure becomes what? 0. That's the meaning of phase difference of pi by 2 between sine wave and cos wave. And you can understand this whole thing with the help of superposition of waves, which we will see later, but we have done a few questions of superposition in simple harmonic motion, and therefore I hope you can understand. Suppose we have a particle over here, and this particle, there are two sources, identical sources. These are two identical sources, and you have a thin film, something which can sense the pressure, and you can also see its displacement. These are two identical sources, and this thin film is placed exactly midway. This and this, they are equal distances. If a command of, let's say, the command is sent in this direction, that move 2 millimeter. Remember, that's how we develop this equation. So source, this first source S1 and this is S2. This first source sends a command that everything should move by 2 millimeter. Then all these molecules, all these air molecules, they will start moving by 2 millimeter, 2 millimeter, 2 millimeter. By the time this command reaches this position, this film will also move 2 millimeter in this direction. If only S1 is present, there is no S2, then after some time you will notice that this film moves 2 millimeter. That's how wave propagates. Now, I told you that this S2 is also an identical source. What it does, it sends the same command of 2 millimeter at the same time, but in this direction. So, by the time this 2 millimeter command arrives at this position, this 2 millimeter command will also arrive at this position. So the thin film is being asked to move 2 millimeter in this direction. At the same time, it is being asked to move 2 millimeter in this direction. If I ask you what will be the total displacement, you will say that this film is not going to move. 2, 2, they're both being cancelled. If you switch on both sources at the same time, then you will find that this fill or all the molecules present over here, they're not going to move. But now understand the whole part in terms of pressure. Well, you can feel the pressure part when you say something. If you put your hand in front of your mouth, you will find the change in pressure, the variation in pressure, you can feel that. Now, this source and this source, they're also sending what? Pressure waves in this form. As these molecules move, you know that when these molecules move, they create what? Pressure. So, the pressure when reaches from this part over here, same pressure command is going to reach at this thin film. And in terms of pressure, if I ask you, somebody is pushing this film, at the same time some other person is also pushing the same film. If you push it from both sides, if I push this thing from both sides, suppose I keep your hand, if I keep your hand between my hands, and if I start pushing it from both sides, your hand is not going to move. Your hand is not going to move, but it is going to experience what? Maximum pressure. That's what is represented by a phase difference of pi by 2. You can also develop the whole thing mathematically, but we'll see that in some extra lecture. Right now, the thing which we are interested in is this part, when it finds that S is 0, it finds that P is maximum. That's the meaning behind a phase difference of pi by 2. Now, for schools and all, we are mostly interested in these forms. Transverse equation, all the particles, they are oscillating. Remember, this peak is up to here only. Just to emphasize, I have drawn it like this, but everything, this is the x maximum amplitude. All these particles, they are oscillating like this, that's the maximum. In this, they are oscillating in this form. Equation is given by a sin omega t minus kx. In case of a sound wave, molecules are oscillating in this form. That's the displacement form, and this is the pressure form. Remember, first important result, and the second important result, phase difference of pi by 2. Note down everything. Let's see velocity of a transverse wave in a rope. We have a rope string. You're producing waves at one end, and these waves are traveling, and we need to find velocity of this wave. The first thing, velocity of a wave in a rope, it depends on two things. First is the elastic property of that rope, how elastic it is, and the second part is decided by its inertial property. Elastic property and inertial property. What are these properties basically? If you're sending a wave in a rope, if you are sending a wave in a rope, let's say this is the rope, and if I keep it in this form, it doesn't have any tension, it doesn't have any restoring force, and if I try to produce a wave, it's very hard to develop that wave. But if you keep it tight, and then if you try to produce a wave, it can travel along the length. Wave can travel along the length. So you need to have what? Tension force. This tension force in the rope decides the elastic property, and mass per unit length of the rope, it gives you the inertial part. Inertial part means all these molecules, they are at rest. Now, how will you move a molecule or the particle of the rope in transverse direction will be decided by the inertia of that particular particle, and that inertia is given by mu, which is mass per unit length. And elastic property is given by F, which is the tension force. Now remember, we use capital T for tension, but in waves and oscillation we also use capital T for time period, and therefore we will take F as what? Tension force. This F, it gives you the elastic property of the rope. Mu, it decides inertia of the rope. These are the two things. We say that velocity of a transverse wave is a function of tension force present in it and its mass per unit length. If again you have a rope which has no tension, do one thing: take a rope and place it on a horizontal surface and have no tension at all, keep it loose. Try to move one end of it, and you will find that these oscillations, they are not able to move along the length. They will simply die out within 5 or 6 centimeters if you produce small oscillations. But keep it tight, and then try to oscillate one end, and you will find that wave is traveling along the length of the rope. And if you take a rubber band, you can observe the whole thing in much better way. I'll show it to you. If you can see this rubber band, I don't know if you can see it or not. I have a rubber band in my hand. If I keep it loose like this and I try to produce waves, then you can see that it's a very small length, and therefore it's very easy for some energy to move from one point to the other point, but it's very difficult. If you keep it tight, you can see the waves being produced, and waves are traveling in this direction. You can hear the sound also which these waves are producing. So this tension force, it decides the elastic property, how elastic this thing, and mass per unit length, how heavy the rope is, will decide its inertial properties. We are not interested in the basic fundamental method for V. Again, if somebody is interested, just let me know. I will tell you how do we get V as a function of f and mu. Right now, we are interested in the school level part, and in that school level part, we say that we will find V with the help of dimensional approach. So, pause the video. I'm giving you a question. V is velocity meters per second. F is tension force Newton. Mu is mass per unit length. Mass kg per unit length kg upon meter. With the help of this information, using dimensional analysis, establish a formula for V in terms of f and mu. If you cannot, come back and see the solution. So what we are going to use, we'll write that V is some constant K, F to the power A, and mu to the power B. This K is a dimensionless constant. Remember, it's not angular wave number. This K is some dimensionless constant. V is a function of tension force and mass per unit length. Now what is V? Meters per second. Meters per second. K, no unit, no dimensions, leave it. What is F? Newton. What is Newton? M into A. What is M? Kg into A. What is A? Meter per second square. Or you can directly use MLT minus 2. But let's write down in this form. This whole thing to the power A. What is mu? Mass per unit length. What is that? Kg divided by meter to the power B. That's how you will write the whole thing using dimensional approach. Velocity m into A, force, mass per unit length, mu. Now, what is meter per second? LT minus 1. What is this? M L T minus 2 to the power A multiplied by M L minus 1 to the power B. This whole thing becomes this. Now you know the next step. Let's collect all these powers. There is no mass present on the right hand side, and therefore for M, if you go for M, mass, on the right hand side there is no mass, and therefore power is what? 0. On the right hand side, let's save time. What is the mass? M to the power A, M to the power B. That gives you what? M to the power A plus B. I hope you're getting this point. There is no mass, 0. Mass over here is what? To the power A, to the power B. You're multiplying these things, that becomes M to the power A plus B. You're comparing both these things. Next, instead of comparing L, let's directly compare T. If you compare T on the left hand side, if you go for T, and on the left hand side you can see that power is what? Minus 1. And on the right hand side there is no T, but T is present over here. And what is the power? Minus 2A. This gives you minus of 2A. Now once you get minus 2a, you got the value of a as what? 1 by 2. If a is 1 by 2, then you know that from this, you're getting b as minus of a. B is what? Minus of a. This gives you b as minus half. Now once you got a and b, put these values in this equation and it becomes v equals to k f to the power a mu to the power b, which is v equals to k times root over f by mu. This k is 1. Experimentally, when we find k, its value is coming 1. This gives us velocity of a transverse wave in a string with tension force capital F and mass per unit length mu. That's how we develop it. Very easy thing. Remember these parts, that velocity of a wave, transverse wave, it depends on what? Elastic property of the medium as well as inertial property of the medium. Elastic property is given by tension force and inertial property is given by the mass per unit length. And with the help of this dimensional analysis, we obtain V as root over F by mu. Note down this much. Now let's see velocity of a longitudinal wave. If you consider sound wave, then just like waves in a string or a rope, velocity of sound in a medium depends on the inertial property and elastic property. Inertial property for a medium is represented by density. For a string, we discuss mass per unit length. For something having volume, we go for mass per unit volume, which is what? Density. Elastic property for a rope was given by tension force. For sound wave which moves in a gas, for example air, that elastic property is given by the bulk modulus. Now what is bulk modulus? B. What is density? Rho. We have discussed bulk modulus in this form. Bulk modulus is delta P upon delta V upon V. Change in pressure divided by change in volume divided by the original volume. We also see in the differential version that was minus of dP upon dV upon V. This is something which we already seen. Bulk modulus. Now, I'm leaving this task up to you. Again, using dimensional analysis, you will write V as a function of bulk modulus and density. You know the unit of bulk modulus. This is dimensionless number. What is bulk modulus? Change in pressure. What is pressure? Newton per meter square, force upon area. Density, you already know, volume. Mass divided by volume. Using dimensional analysis, you will arrive at this result. Root over B divided by rho. For rho, this thing was F, tension force. This thing was mu, mass per unit length. For a sound wave traveling in a medium, velocity is given by root over b divided by rho. I hope you can do that. If not, just let me know. Now, once we found this formula, there are two versions available. First thing is Newton. Newton thought that when sound propagates in a medium, it is an isothermal process. When sound propagation takes place, according to Newton, it is an isothermal process. Isothermal means when these air molecules they are oscillating, he assumed that temperature does not change. It remains constant everywhere, every time. During the oscillation process, that temperature is not changing. Once he thought that sound propagation is an isothermal process, we have seen in mechanical properties of matter that for an isothermal process, bulk modulus is given by P, pressure. It's not change in pressure, it is what? P. For an isothermal process, you can see the notes of mechanical properties of matter where we have discussed the whole thing. For an isothermal process, your bulk modulus is what? P. If bulk modulus is P, then according to Newton, velocity of sound wave should be P divided by rho. But experimentally we found that this thing is not giving us the correct result. When theoretically you develop V, velocity of sound in air, using this formula, then it doesn't match up with the experimental data. So Laplace came and he said that sound propagation is so fast, these oscillations are so fast that these molecules or atom or the particles, they have not sufficient time to exchange their energy with the surrounding. These oscillations are happening so fast that you cannot transfer energy of the volume through which sound is propagating. And if you cannot transfer your energy with the surrounding, I hope you know that the type of process is called an adiabatic process. Adiabatic process. So according to Laplace, sound propagation is an adiabatic process. And if it is an adiabatic process, because no energy can be transferred, again in mechanical properties of matter, I have told you that bulk modulus for an adiabatic process is given by gamma P. Bulk modulus for an adiabatic process is given by gamma P. If this is gamma P, then velocity of sound should be gamma P divided by rho. And this result is in perfect, the result which you get using Laplace correction. This is called Laplace correction. The result which you get using Laplace correction perfectly matches up with the experimental data which we obtained for velocity of sound in air. And therefore, originally the whole thing was given by Newton, but Laplace corrected the whole thing, and therefore this is called Laplace correction. Remember, this is Laplace correction, which is the actual formula for velocity of sound, given by root over gamma p divided by root. Now, we can write this whole thing in terms of temperature also. How will you write the whole thing in terms of temperature? What is P? PV is N R T. What is N? Number of moles. This is number of moles. How do you define number of moles? Mass divided by molecular weight. M divided by M naught, molecular weight, multiplied by R into T. This gives you P into V divided by M as RT divided by M naught. What is this? This is P divided by M divided by V. What is mass upon velocity? Mass upon volume. Mass upon volume is density, rho. And therefore, P upon rho, it becomes what? RT divided by M naught. And this formula of V should also be remembered in this form. Gamma, adiabatic gas constant, multiplied by R T divided by M naught. Now remember one important thing. This T is not in Celsius, this T is in Kelvin. So if somebody asks that what is the velocity of sound at 0 degrees, so at 0 degrees you will not be putting 0, you will be putting what? 0 plus 273. This capital T, remember, is what? In Kelvin, molecular weight of the air or the gas in which sound is propagating. That's how you write velocity of a longitudinal wave, which is sound, in a medium in terms of its inertial property and elastic property. Note down everything.